In this video, we're going to address a subscriber question. That question was, how do we verify requirements that has textual constraint and not numerical? For example, the requirement says the indication light shall be turned on when the car door is not locked. How do we verify this requirement as we do not have a numerical constraint? And so he had this question from the automatic constraint creation and text read video. And in that video, we had several different examples, but basically we're trying to show that Cameo can automatically read the text, such as B and then a number, and attach that to a value property. And then when we run this in simulation, you can see that the requirement is satisfied because it's green. And if I change the number to like 6 or something, then you hover over it and it says it is not satisfied. If you want more information about the automatic text read function, please go back and watch this video right here. But let's go ahead and get into some of the examples which we're going to use to help answer this question that was posed. So jumping into example 1, we have created the requirement as in the question. The indication light shall be turned on when the car door is not locked. And we have derived two different requirements from that. One about the indication light and one about the lock status. So right now I'm just saying it should be equal to 1, which would mean true, or should be equal to 0, which would mean false. So essentially we just did two derived requirements here. We have our system of interest, our car, with the indication light as one of the part properties and the door as another part property. These have value properties underneath them, which are just integers right now, 0 and 1, true and false. And then we've got the satisfy linkage between the value property and the requirement for both cases. When we run this in simulation, you can then make it a little bit bigger and see that both of these are set to true, meaning that they are satisfied. The problem with this is that they are independent. So there is not this if-then sort of ability. What I mean by that is it doesn't solve the problem because the two requirements are not connected. It's supposed to be the indication light shall be turned on only when or if the car door is not locked. So we can find a scenario where, okay, the car door is locked, so the car door is locked. That shouldn't, the car door should be allowed to be locked and they're not throwing an error. So because these two requirements are not connected, it is not a proper solution. We also notice that we're using the satisfy link here, and all of the linkages that were explained in this automatic constraint creation are satisfy linkages. The question posed is talking about the verify linkage. We'll get to that at the very end, but for now, we're going to just walk through the satisfy linkage. Moving on to example 2. The way to do this if-then is you would create a constraint. So right now we've got our same breakdown, our car with our indication light and our door with our value properties. We've got the satisfy linkage between the constraint and the requirement, and then we have applied this constraint to the car, the system of interest. And then we also created a parametric diagram that is going to connect the constraint parameters to the value properties as you would see here. Doing that whole thing will allow us, when we run it in simulation, to have that if-then statement working appropriately. So we have, we can sit here and change the values for here. So this is the bad case, where if the indication light is off while the door lock status is false, so it's unlocked, then that's an error. But it does allow us all the other permutations. So we got 3 green permutations and only 1 red permutation for our if-then statement, which is as we intend. Now, the way that we created this constraint was we just added a constraint block, and then we went into the specification of the constraint block, and you can just go look at your constraint, and there should be, here we are, constraints, and you'll hit 3 dots, and then you can add in your line of code here. And that's just my if-then statement. So if door lock status, which is a value property, equals 0, then you'll do this. Otherwise, it's true, meaning that it's a pass. So if door lock status equals 0, then you would go in and see if the indication light status equals 1. If both door lock status equals 0 and indication light status equals 1, then return true or pass, otherwise return false. So, and we're just using the language of English here, and it works. So this would be the quick solution. Now looking into example 3 and 4, all we're going to do is, instead of using integer, we're going to be using Boolean and then enumeration. So we'll look at Boolean first. So the difference between example 2 and 3 is that we're using a type Boolean here. So true and false versus 0 and 1. We've got our Booleans down here for our constraint parameters, and we've changed the equation just a little bit so that it doesn't say 0 and 1, it says false and true. When I run this, you see that it also works as intended, where I can go in here and modify my true false values to have one set that's false and then 3 that are set to true. So pretty straightforward there. The next example 4, instead of using the Boolean, we can use something that's even simpler to understand, but harder to implement, meaning this is the enumeration. So instead of having true, false, we have these enumerated values. So we have 2 different options, or from our drop-down list view, on and off. So indication light on, the door lock status is on or off. So you can do this as well, and then here would be the if-then statement. And so it does work this way as well. So I'm running it, and I can come down here, and you'll see that I now have my drop-down list view that I can change, and you see that it appropriately has one of the 4 permutations does not work. So looking into example 5, we're actually going to be adding behavior into the previously only structural diagram in simulation. So we have 2 state machines that we would be running. So when we push this second play button, we're going to be running the behaviors as well as the structure. So we've got our structure right here and our behavior over here. What that's allowing us to do is basically force this if-then statement or logic to occur through our behavior. And so, for example, I can now send the light off command, and you'll see that the value property changes appropriately, the state changes appropriately. I can click on the lock status and I can hit the door unlocked signal, and you'll see that it's now in the bad situation where both of them are off, so it's no longer successful. This constraint is not passing. But this is the first step to essentially modeling out the constraint. The intention here is that as we step forward, we will create a behavior that does not allow for the requirement to fail. Our next step is going to be looking at example 6, which is going to be adding the internal block diagram so that we can communicate between the car block, the indication light block, and the door block, as well as the classifying behavior of the car block. So we can connect and communicate between the car block's behavior to the indication light's behavior to the door's behavior through the internal block diagram. So when we run this, we push play, and you'll see that the signals are being sent, and that is changing the states of each of these nested part properties, and we still have our constraint here. And so if we stay at the car level, we can send the unlock command, which is going to transition us at the car level from car locked to car unlocked. And then it's going to kick off this activity right here. So this activity is kicked off, and for a brief second, we have both lock status off and the indication light status off. But then it goes on to the appropriate situation where we have lock status equals off and then indication light status equals on. So I'll try and resize this and just do that same thing again. So now we can see the whole thing at once. I'm going to replay running the car block in simulation. So I'm going to click start, and then if I hit the little arrow enough times, I can see what signal I need to send. So I'm going to send the car unlock command. So I send the unlock command, and then this kicks off. And there's that brief second that I was in a bad state, but then it goes to a good state. The reason why it went to that bad state is because I sent the door unlocked command before I sent the light on command. If I had reversed it, then you would not see the error at all. So I'll go ahead and just do that really quick. So now we'll go ahead and rerun that car block in simulation again, just as before. This time, when I send the unlock command, you'll notice that these never turn red because it never goes to that false state. So essentially, because these never turn red, I've created a situation where the behavior does not allow me to incorrectly or not satisfy this requirement. Now we'll look at example 7, which is exactly the same as example 6, except for the fact that instead of having the state machines down here, we have activities. with opaque actions. These are opaque actions down here, the status, and it's basically just going to have a line of code in there and under the body language, which is going to reassign the value property. So one is not better than the other. I'm just showing that there are two ways to do this and that both work as appropriately. So we'll just kind of watch this work. So we'll send the unlock command, and you'll see that briefly it changes to that bad state and then jumps back out. And that's because we hadn't switched around the order of these two send signal actions. If we were to do that, then again, just as before, it would just remain green or satisfied throughout the entire activity. So now we'll look into example 8, which is constraining on state. This one admittedly needs a little bit of work because it doesn't currently work. That doesn't mean that Cameo can't do it. That just means that I haven't been able to figure it out, unfortunately. Basically, when you run something in simulation, you have this console where you can actually add lines of code, and it will give you feedback appropriately. So what I can do is I can use different commands and see the current status of the system of interest. So what we'll do is run the car block in simulation, push the second play button, which will start the behavior. And what we can do is just copy this line of code right here, Control C, Control V, make sure our language is set to Python, and hit enter. And you'll see that it gives us the true value. So what this is asking is look inside of the light part property, which is going to be looking into indication light block, and determine what the state is, and if that state is equal to off. And so we see that the off state is the one that we are currently on. Therefore, the answer is going to be true. So if I send the unlock command, you'll see that now the light status state is on. So if I rerun this line of code, it now tells me false, meaning that it is no longer in the off state. So what I tried to do was just make that the constraint that satisfies the indication light state requirement, but it just didn't work for me. The reason why I would want to do this is because it's no longer tied to value properties. Notice we don't have that status value property underneath here. And that just makes it a little bit simpler if you've got just tons and tons of these requirements. So I've listed a couple other different lines of script that you could test and play with in the console. But if you find a solution, please let me know in the comments. Unfortunately, I wasn't able to find a solution super quickly. So that leads me to example 9, which is the simple satisfy solution. And basically, what I'm doing is actually taking away the constraint completely because I've kind of coded it out. As we showed before, like I said, coded it out. I mean, the diagram is not allowing, the behavior is not allowing for the system of interest to go against this requirement. So therefore, I can just say that this activity right here, which is sending the door unlocked signal and the light on signal at the same time is going to be satisfying this requirement. And just call it done there. We don't have to have the red green checkbox. Like there's no requirement at all. It's just the behavior itself that have been modeled are going to satisfy this requirement. And I would call this good enough. So I can send my unlock command. Both of these guys get sent at the same time. You see that my door is set to off. My indication light is set to on. So everything's good to go. And now that we are here, which is this is where I would normally model to with the satisfy linkage when you don't have like an actual number to reference. So now to get to the verify aspect. So we'll open up example 10. And the difference is that I've added this test case. And so this interaction was created automatically using our simulation toolkit. So we'll go ahead and do that again. And this interaction is going to verify that requirement. So if I push play on the car, so before I start the behavior, when I click that, it's going to start the behavior. Before I do that, I'll right click on the car down here and then do create sequence diagram. So it's blank right now, but as I push play and everything else goes, you'll see that it will start populating. Now I realize it's kind of hard to see here, so you're just going to bear with me. I'm going to push play, and now you'll see that the different states are being shown on my sequence diagram, and I can go down here and send the unlock command. The user sends the unlock command. The door unlocked and light on signals were sent, changing the states of the door and the indication light. I can then, turn it back to locked and then turn it back to unlocked. And the act of doing this test is going to verify that this requirement was satisfied. So I'll just push stop here, and this is where it lives in the containment tree. So this system car at the date is this diagram right here. So if I double click here, you now see this. You can go into the requirements diagram, and then you can find the interaction here. You can pull that onto the diagram, and then you can add your verify relationship between your interaction and the requirement that it's verifying. So I've done this twice now, so these are redundant. So I'll just go ahead and delete the ones that we just added, and we're good to go. So if I double click here, you can see the state machine diagram. You've got down here this test case activity, state machine, or interaction. So if I were to make one of these test cases, it would look and feel like this interaction, except it has one additional thing to it, which is the verification, the passed, failed, inconclusive. So if I just do like a test case example, and then I just create a diagram. You see that I have this return verdict. So this would be the return at the very end that you could add. And if I look up what about this verdict kind, I can read about it in the auxiliary resources. So essentially you got pass, fail, inconclusive, or error as the four different enumeration options that you have in your drop down. So if you don't have something that's just like this right here, this just proves it. So like if it makes it through this, then to me that's a pass. But sometimes like you might have multiple paths for like an activity diagram. And so then you can have a test case that's an activity diagram. And then you would show that verdict kind over here. So I'll quickly build out an activity diagram that has the happy path and the bad path. The happy path is going to result in a passing test, and the bad path is going to result in a failed test. You'll see that in simulation. The first time I run simulation, I take the happy path, resulting in a pass in the bottom right. The second time, I take the bad path, which results in a fail, or red in the bottom right. We hope that this video has helped explain both the satisfy relationship and verify relationship in simulation, and has helped answer the original question. If you've got more comments or questions, please leave them below. Thanks for watching.